Sorry, everyone. We're going to make this video on demand, make this webinar on demand. So we'll begin recording it. Um, so that's myself. Our other speaker today is on the right of your screen, Ricky Vesel. I'll give him just a moment to introduce himself if he wants to speak.
Hello, everybody. Greetings from South Florida. I have been working with Griffin for about 6 years. Actually, the project that I started with was the one that I'm going to be showing you today. I started hacking on it about 6 years ago, and I pretty much rebuilt it from scratch and have been doing maintenance and modifications on it here and there since then. So I'm going to be going over that. Besides Griffin, I do software development, some entrepreneurial software, and down here in Boca Raton, enjoying the warm.
Some of us up in the northern states are jealous of Ricky, except for the humidity, but that's besides the point. Thanks, Ricky. Appreciate that. So today in our webinar, we want to present to you guys a little bit about this concept out-of-variant control and how that ties in with the Griffin AI Toolkit. The toolkit it's a process optimization platform, and really the main key or feature behind this is that it's an open system, meaning that there's a lot of ability for customization and tailoring to unique applications. And so to highlight or discuss how those two concepts, out-of-variant control and the toolkit itself, are used, we'll talk about one of our reheat furnace solutions. That's the project that Ricky just mentioned, how he has been able, and the Griffin team have been able to use that to help out the reheat furnace. And then I will talk a little bit about mercury and pack control. Another application where we've utilized the Griffin toolkit to enhance just standard DCS control to make it more capable and provide overall improvements at a facility. With those items discussed, we'll then move into our discussion portion of our webinar. As mentioned, during this time, anybody wants to make a comment or ask a question, please just send something very quickly to the chat window, and I'll enable you to start speaking. Or you can go ahead and just type your question to the chat window if you're more comfortable with that. Then after we complete that discussion portion of the webinar, I'll talk a little bit about how you can use the Griffin AI Toolkit today, how it's immediately available, some of the options we have to get it in your hands so you can explore it. So I'll jump right into a little bit of background on the Griffin toolkit, starting with the Purdue model of ISA 95. Those of you familiar with control are likely familiar with this structure. It's kind of for long been regarded as the gold standard of process control. The plant communicates, excuse me, let me get the laser pointer so you can see where I'm pointing. The plant level in the field communicates with control devices, communicates with supervisory systems on upwards to coordinating computers, and then the overall production scheduling level. This has been in place for numerous years, but over recent years, with kind of the data industrial revolution of big data, artificial intelligence, industry has evolved, and we at Griffin believe that this structure needs to also evolve. And in order for that to occur, we've identified and coined this term out-of-variant control. And what it is, the reason we've done this is there's a need for this intermediary level between supervisory systems and overall production control at facilities. In the out-of-variant control level, we regard as an artificial intelligence operational assistant, better acting as a bridge between those two levels in the Purdue model. More specifically, out-of-variant is a word you've likely never heard. It's derived from Latin, the Latin term meaning to assist. And And what we are referring to when we mention add-a-variant control is exactly that, a system that assists both operators and the control system, really to synergize those two, bring out the best of both of those factors to make them operate as well as they possibly can. So our add-a-variant control builds upon as I mentioned, a very open, customizable platform, bringing to the table artificial intelligence capabilities, as well as more traditional PID, feedback, if-then type of control methodologies. The other key thing that we have developed to go along with this add-a-variant control is an intuitive framework for anybody to immediately interact with the system and develop logic and control, all while maintaining this underlying key concept of bridging the gap between systems and people. So Griffin itself it's a toolkit. It really is. It's really a tool belt you could think of, brings to the table many different techniques and abilities to implement different flavors of control between a resourceful, the word escapes me, but a resourceful and flexible person and a rudimentary, robust DCS control system. The toolkit acts to bring out the best of both of these people, allowing for knowledge of people to be gathered and captured inside of a control system, while also maintaining flexibility and robustness that the DCS provides. And so all of these things, that's really what Griffin is. Griffin itself originated, or the Griffin AI Toolkit originated about 2013 by recognizing that there was a gap between these two levels of control, DCS, supervisory control, and the operators themselves. Our founders, Brad Radel and Siva Alagasarmi, who are on this call, recognized that there were so many things that both sides of this bridge said, well, if the other side could just do this, it would make our lives easier. Or if we had the ability to make the control system act like this, we could implement more robust and effective control. And that's really what led to this development of add-a-variant control and the Griffin AI Toolkit. And so we're going to go through, as mentioned, one of the large and really, I would refer to as an impressive application of the toolkit in a reheat furnace, kind of demonstrating many of the concepts of advanced control, as well as base systems knowledge and expert knowledge integration into a system. And for this, I'm going to turn the time over to Ricky, allow him to present on that application.
Thanks, Jake. So I'm going to be talking about temperature control system for a large-scale steel reheat furnace. And I'm going to pull up our graphic. This is a nice visual representation of what's going on in the furnace. On the left, we have, oh, sorry, are you sharing my screen? Am I sharing my screen?
I do not see it yet, Ricky.
Let me pull that up. All right, you with me?
Yep, we see it. Thank you.
So this is the main graphic that we built for this application. Of course, if you're going to be building custom graphics, that is going to involve writing some code. So we coded this up in Java. It's on the left here is basically a to scale physical representation of what's moving through the furnace. Each slab here is a piece of steel weighing around 40,000 pounds. And we have our aim temperature at a certain stage of rolling, residence time, predicted residence time, and colored according to temperature relatively accurately. And on the right here is a very important addition to this visualization that I created, which shows a % of readiness extraction, where red slabs are not recommended to be extracted. Yellow slabs can be extracted, are predicted to come out below aim temperature when the temperatures are validated physically. And green slabs are predicted to be at or above desired temperature. And I'm going to talk about some of the aspects of this project, how the features and tools available within the Griffin AI Toolkit contributed to what I did, some of the challenges and achievements, and I'm also going to walk you through the application itself a little bit to give you a look inside Griffin and see what the code actually looks like, or the logic, I should say, because it is not in fact code. So let's look at this here. So I want to talk about some of the features of Griffin that were fundamental in this project. First of all, it's the separation from the DCS. When you, in combination with the ability to rapidly prototype, you don't really want to see rapid prototyping within the DCS, because the DCS contains your safety critical control systems designed for safety and reliability. Using Griffin, you have this more flexible layer that can communicate with the DCS, sitting sort of on top of it, in between the operator and the DCS, doing ultimately a lot of the things that operators would normally do, or that you would want operators to do, doing it with greater consistency and more accuracy. Another hugely important feature of Griffin is the completely built-in nature of neural networks. I use neural networks all the time. When you change the ease of use of a tool, you often change how that tool is used. With neural networks and artificial intelligence in general, they're often looked at as kind of something that you need to bring in an expert to assemble this black box neural network, and then you can plug into it and maybe get some use from it, and it might become stagnant over time and lose its usefulness. That's not how it works with Griffin. They're completely accessible within the toolkit. We have supplementary tools for building neural networks quickly and easily using a visual graphical user interface. And so I use that, I lean on that a lot when I'm developing Griffin applications, even as an alternative to developing something like a simple model where a linear or polynomial fit might be adequate. Instead of doing that model building manually, you can quickly plug the data into a neural network and get almost an equivalent model much more easily. I would also say that this platform, Griffin, so I use Griffin in the field, and I also do software development on the Griffin toolkit. And we basically designed this toolkit specifically for process optimization. That's what we use it for. And so everything in it is geared toward that goal. And also, if you get into some applications where you're needing some functionality that isn't available, Griffin is very customizable. We are adding new components, new pieces all the time, and customers are able to do that as well using templates that we can provide. Talk a little bit more about neural nets, also with reference to the concept of digital twins. In this application, I use neural networks to predict the slab temperature, the measured slab temperature at a certain stage of rolling, which is basically their KPI for this furnace. And I have two different levels of complexity of the neural nets that I use. One is very simple, kind of that basic fit model I just mentioned, where I look at the slab geometry, height, length, width, weight, and I also look at the temperature that we calculate for the slab when it's extracted from the furnace. And I use that. That's only about 6 or 7 data points, and I plug that into the neural network, and it's going to spit out the predicted temperature at a certain stage of rolling. I also this model, if you apply error correction to it, in other words, you're likely to see a steady state error over time. If you're rolling 100 slabs all in sequence, you might see a 20 or 30 degree error from the output of this model. But if you bring that error back into your back into your application and incorporate it, you can account for that pretty easily. Where this model tends to fall down is when you're transitioning between material types and also target temperatures. As you're moving around, that error term is basically going to change unpredictably. And that's where we were starting to see problems where if we're going from high temperature to low temperature or vice versa, it's taking longer than we thought, or we're dropping down too much in temperature and having swings. So what I did was build a second generation neural network that took in a lot more data, basically looking at a time history of temperature sensor information, as well as the time history of the calculated slab temperature moving through the furnace, and incorporating all of that into a prediction of the measured temperature at a certain stage of rolling. And this model is actually a little overcomplicated, I would even say, to the point where if we're in steady state, I'll resort back to the simple model. But if we're going through transitions, then I will refer to this model, and this will give us better performance during the transition. And I also use neural nets to model the temperature sensors. We have a group of temperature sensors that are controlling. They are what are giving feedback to the burners to call for more or less heat. And we have several other temperatures in the furnace that are not controlling. And if I am predicting, if I'm trying to simulate the slab moving through the furnace, which I do a lot in this application, I want to calculate which temperatures are going to give me the desired temperature after the slab goes out of the furnace. So I know what temperatures I'm going to call for the controlling thermocouples, but I also need values for these other ones. And so I use neural networks to fill in those blanks. And we'll talk a little bit about digital twin concepts. So I'm going to show you again our graphical representation. As far as digital twin is concerned, the digital twin concept is valid at many levels of complexity or detail. I mean, you can draw a picture like we have, or you can go farther. You can have a physical model of the heat distribution through the slabs, which we also incorporate. You can have a neural network process model. You can be trying to model the molecules down at a quantum level of every piece of material in your system. Obviously, there's going to be a point where the trade-off between more model complexity, more trying to further mirror the physical reality you're gonna hit roadblocks. So I'll show you where we ended up with this project as far as the digital twin is concerned. So let's look at the application. I'm going to go back to this graphic. So now that we have some context, we have the steel moving through the furnace, and we have this display here showing percent readiness. The white lines are kind of the anticipated or planned temperature versus 100% readiness. As you see, these slabs are all ahead of anticipated, and that's because they've been sitting longer. Maybe we're on the red light right now. This, by the way, is this steel furnace temperature control application running in simulation mode on my computer. So what I did was in Griffin, I created another application. This is the demo simulator, and I designed it to basically read in data files pulled from on site and output that data so that it can be read by our actual control application, which is here. So this is our actual temperature control application. It has quite a bit of logic. I'll go through some of the tabs here and let you know what's going on with it. And I'll also point out that this list here, this furnace opt, all of these components are components that were custom built for this application. If we were to do it again from scratch, we might not necessarily need some of these. Some of these are like this walk, charge. These represent events that we receive from the plant. And some of the others are encapsulating more complex functionality, like the slab optimization. That's a component that will calculate optimal temperature set points for desired slab temperature. Okay, so yeah, let's look at the logic a little bit. I'll show you what I first started with on Griffin back in 2015 was basically this sheet right here. And the idea of this sheet was to take the temperature readings that we get, which are our key performance metric for the furnace performance. And I do have those in one of my graphics here. Okay, so this is called the R5 scan. Temperature scan, each of these points represents a temperature value read from the slab. And as you can see, even from a single slab, you're going to have pretty widely varying temperatures, which is part of one of the challenges of controlling this process. But basically, we wanted to take this array of temperatures, and some of these will be, this might be filtered here, I think, but some of these will be way off the chart, low. They might be 500. At the edges of the slab, you'll get some anomalous values. Basically, taking these values, filtering them, processing them, and assigning them into 1/3 components of the slab to look at like the head, mid-body, and tail temperatures as they vary over time. So this type of logic, I mean, this one page was a project for me in Griffin that probably took a week of building this out and testing it. And then as far as the rest of this application is concerned, I probably spent about another year rebuilding this whole thing from scratch. We had a different solution in Griffin for this temperature set point control that wasn't quite behaving how we wanted it to, so we ended up starting over. And I've also been building on this and modifying it here and there over the last few years. So one of the nice things about Griffin is that it shows you real-time logic execution. So this red line here is showing us the execution path. This logic here is determining what mode the furnace is in. So mode 0 is off, mode 2 is warm up, 3 charging, 4 run out. And we are in mode 1 for production. And when you're having issues or debugging, this is really helpful as far as understanding what a visual or graphical logic programming application is doing. We also have functions where you can go to this block. This is a function call block or a jump to. I don't use the jump to very much, but I do use the function call blocks, which I believe is this one. Yep. So we're calling this function slab profile charge, which is probably this one down here. So at a certain point in the logic, we'll execute this, and depending what furnace number we're in, these are neural network consult blocks. So these are going to consult a neural network. And we have the inputs, which are real-time data. And then this block is going to output a value from our neural network. And when this thing is fired up and running, it'll look a little something like this as far as the visualization of the furnace process is concerned. So this is sped up, I don't know, probably 200 times or something like that. You can see the steel heating up and getting processed through. And I'm going to go back to my slides and talk about some of the challenges with this particular process. So a big one was building the behavior to meet operator practices and expectations. And this is where the rapid prototyping and flexibility of the Griffin platform comes in handy. Because while I was working closely with the crew there, it comes up over and over again because you don't get the complete picture the first time around. And you'll encounter some sort of edge case where they're expecting a particular behavior or some problem is being created because of the way you handle things. and you need to modify the system. And quite often I was doing this, making significant changes and modifications live on the system while in production. And I mean, when I say significant changes, I'm talking about putting in something like I don't know, an entire section of logic, like this. So this is our pacing system, and the problem this was designed to address was we were getting, well, first we were, even though we improved the temperature set point control, we didn't really have any management of how the plant would extract from the furnace. So they might be pulling slabs out, even though they're in the red down here and not up to temperature, they could still be pulling them out. So eventually we put in a feedback mechanism where Griffin was able to send a signal to the plant saying, the next slab is not ready, so don't pull it. So that was a feature that I added probably real time on the fly. And then we said, well, that's working okay, but what's happening is we're like all of a sudden getting to a point where we have to sit and wait 10 minutes or 12 minutes for a slab to get up to temperature. And that's not going to work because they want the process to be consistent. They want to keep rolling. Their equipment drops in temperature if we're not rolling steel through it, and it causes other problems. So what this logic here is designed to do is basically look into the future and look at the readiness of each of the slabs and space out the extraction of the next to extract 5 or 10 slabs, such that we always have ready steel and we're not having to sit and wait for an undue length of time for a single piece to heat up. So this pacing system was something that I developed in production, tested it, modified it, all live. And you can see it's a significant amount of logic. And that's easy to do. It's easy to do with Griffin. And that's part of the benefit of having this as a completely separate platform from the DCS, where the basic safety critical systems are not really being touched. Some of the other edge cases that we ran into after time where the system in production, we had melting steel. So originally I had kind of conservative temperature limits, like we wouldn't go any higher than 2,400 degrees on the temperature set point. But then I saw operators taking the system out a lot and putting it into like 2,440. And I said, well, I thought we agreed that we weren't going to go over 2,400. Well, that's where the idiosyncrasies and the day-to-day practices of operators can diverge from the engineering staff and other personnel that you might be interacting with. So they were telling me that, no, that's normal. We put it up to 2,440, especially if we're falling behind or whatever like that. So I bumped up the temperature limits to 2,440 because I'm trying to get this to run as fully automated as possible. And then it turns out another day we're sitting there at 2,440 and the steel starts melting and dripping down into the underbody of the furnace. That's clearly not desirable either. So I had to put in a whole different set of logic for checking steel temperatures and making sure they weren't going out of bounds. Temperature alarms were another thing. I discovered some temperature alarms existed only after tripping them with my control system and kicking the furnaces out. So had to make some changes, again, on the fly during production to make sure that if we start approaching high recuperator temperatures, we're going to roll back on particular set points. Roll changes are when you pause the process, put it on hold, and you change out the steel rolls that roll the heated steel. And if I'm aware of those, let's look back at our furnace map. If I'm aware that a roll change is coming, like if this slab is going closer and closer to extraction, I can know ahead of time that this slab is going to get an extra 15 minutes of residence time. So I can allow this slab to be colder in my pacing logic going up toward the exit, and it can even be red by the time it gets up here, knowing that it's got an extra 15 minutes to warm up. And that can be a big process improvement. Because normally I would slow things down to make sure that every piece of slab is up to temperature fully by the time it reaches the extract zone. And also how to handle temperatures during random delays. When a delay comes, you can use it as catch-up time first, and then you're sitting there in maintenance mode. You probably have to cool things down so you don't overheat the steel. And if a delay is going to be really long, you might even consider backing temperatures off to save fuel, of course, with the caveat that you don't want them to have to wait when they do come back online. So handling all of that is, I handle all of those cases a little differently within the application. And there are big conflicting requirements to balance, such as different temperature requirements for slabs. You might have a slab with an aim temperature of 2100 right next to a slab with an aim temperature of 1950. And you're going to have to figure out how to manage that. And there are some serious conflicting objectives in terms of production rate, standing against fuel use and your heating criteria. Right now, they're having an issue. It's probably going to be our next project where actually the pacing logic I was talking about, they're attributing basically too much process slowdown to that logic. And it could be happening. It could be that it's being overly conservative and holding things up when they could be putting more steel through. So we're going to have to take a look at that and try to find the ideal balance of maintaining required temperature as well as moving as much steel through the furnace as possible. As far as what this project achieved, one of the biggest accomplishments was eliminating temperature reject slabs through enhanced automation of the process. With operators, I've been in the room with operators, they've been sleeping or on the phone. Some of them are attentive, some of them are attentive some of the time. No one's attentive full time, and that's kind of what Griffin is about. It's what Jake talked about with adavariant control, where we like to use Griffin to encapsulate operator best practices and automate them. That's a big part of what we do with this toolkit. So a reduction in temperature reject slabs, which should never really be happening. And we did achieve a significant fuel savings depending on the day and how we were looking at it, is somewhere 5, 10, 12%. And yeah, the improved reliability of the process through better automation is something that's a benefit to them. It takes pressure off the operators, and they have a better idea of what they're going to get from this system on a day-to-day basis. So that is the steel reheat furnace project. Jake or anyone else, if you have any feeling about something I can look at more or questions, do let me know.
I just had a comment, Ricky. This is Jake again. One of the things that I think most impressed me when I learned about this project of Ricky's at this reheat furnace was that there, as I understand it, there's no temperature measurements of the steel within the furnace. Is that correct, Ricky?
There's no temperature measurement of the steel itself in the furnace. We calculate these temperatures if you look at the furnace map. So we have a current temperature on here, 2013, and this is this of 2366. This is the calculated desired extract temperature. So this is all based on the heat model, which I think we basically copied the heat model that they had in place there, and we put it in Java and connected it up to this Griffin application.
Yeah, so to me, that's really impressive, that basically creating sensor values from essentially nothing, just using physics-based as well as neural network modeling, a huge asset to this plant in this process for sure.
Yeah, it definitely helps them to get an idea of what's going on in the furnace visually, and this readiness map is what they rely on most heavily, to my knowledge, because this shows the actual progress in a sensible, visual, physical way of the steel as it approaches extract temperature.
Awesome. Very interesting. Thank you, Ricky.
Sure. All right, I'm going to turn off my screen now.
Great. Go ahead and start sharing mine again. If anybody has questions, we do have that Q&A session coming up as soon as I finish my little portion of this presentation. if you don't mind, let's just hold your questions until then, and we'll have a good discussion there. So as Ricky talked about, a lot of success in this application, a reheat furnace, seeing multiple benefits from using out of variant control, using the Griffin Toolkit, really to address different aspects of the process, all with a single objective, but in multiple ways. I'm going to talk about a much simpler system, a much simpler control objective, being mercury emission rates and pack injection rates, minimizing pack while also minimizing mercury emissions to reduce costs, but also to account for the effects of pack injection on the process itself. Just a quick piece of background on this. This isn't a coal-fired furnace. This plant had the requirement to minimize their mercury emissions. And they do so by injecting packed powdered activated carbon. When coal is combusted in a furnace, mercury is emitted. It's one of the constituents, one of the chemical constituents of coal. There's a little bit of mercury in there. And really, when we inject pack, we're focusing on the oxidized portion of mercury. And so essentially, we're trying to absorb out the mercury from the process itself so that it's not emitted to the atmosphere. What's problematic with this is basically we're throwing a whole bunch of black dust into the process, which ultimately affects other emissions and affects the process in a number of other ways as well. Particularly in this application, the opacity readings at the stack of this plant, very clear relationship between higher pack injection rates and opacity rising. And this site had an opacity limit. So you have these competing objectives of we need to minimize mercury emissions, but we also can't have our opacity readings go too high. So we know that our opacity is climbing because of our method of reducing mercury. So what do? How do we best balance these two objectives? And that's really what Griffin is really key, really a good use of the Griffin AI Toolkit. Some background on this problem of this balancing act between pack injection, opacity, and mercury emissions was something that the DCS, the plant engineers at the site, have been working on for months, trying to come up with a good way to address this controls issue. Our system, the Griffin Toolkit, was on site for some other objectives, some emission rate optimization work. And our engineer on site said, well, why don't you let me have just a crack at it, see if I can come up with a control system or a methodology to help you with your pack and mercury and opacity issues. And that's how this application was born, was from that right there. So I'm going to actually break out of the slideshow and open up the application that was built on site. So one of the key things that's important to this was the fact that mercury is monitored on a 30-day average. Their emission rates are a 30-day average, or opacity, 6-minute averages of their opacity reading will cause them to be in violation. And so that's one of the process characteristics that is really difficult to capture in rudimentary DCS control. But Griffin has the flexibility to work with that and to leverage those characteristics. So I'm going to actually start a fast version of this so that we can look at about 60 days worth of runtime. And then we'll look at the actual more of a real time. It's 1 second equals 1 minute, but a simulation view of this same process. So you see we're flying through control over here. But I'm going to now start one that we can kind of watch how the system itself develops. So in Griffin, there's applications, which there can be multiple different applications, or these are basically logic bundles. You could think of them, or packages running at any time. And then there's data links, which communicate data back and forth from DCS or an OPC through Modbus, or can communicate with files as well. This system, it's also a simulation similar to Ricky's. And so I'm communicating with a data file that this application is actually writing to simulate the plant and the emissions from it. So I'll start this up, and it's going to cover up our other values. And we'll see how this thing runs in real time. Take it a second to initialize. So this screen right here, we see the pack feed rate. Right now, this is in DCS control. I have Griffin control is set to off or 0. And you see I'm generating some statistics down here. How much time has gone by? What's the average opacity? What's the percent of time so far that opacity has been greater than 21%? That's right about their alarm level or their violation level. And so you see the DCS has a set point. In our screen right here, the set point for their mercury emissions is 0.8. And so traditional PID control is simply adjusting the pack feed rate to try to lower the mercury emission level, all just a direct one-to-one single input, single output system. You see opacity is this green line. It's fluctuating around, but there is a relationship between how much pack is entering the system and where opacity is going. See that right here, pack increased and opacity started to increase on average in general. Now pack has come out of the system in DCS control, and slowly opacity is kind of rolling out. But we also see mercury will start to trend up. But really what's key in this application, as mentioned, is the time frames that each of these constituents are concerned with. And also the recognition that there are times in the process where just the process itself will emit lower mercury or opacity will be better simply because of the fuel that's being burned or other process conditions. And this whole application capitalizes on kind of the ability to bank up good conditions and then exploit that when conditions are bad. One thing you'll notice here is that even though pack is rising and mercury is rising as well, the 30-day average that's calculated so far for mercury is really low. It's much lower than our set point currently. You'll notice right here, pack has increased significantly, and now opacity is high, and it's continuing to be high. We're spending almost 10% of our time above our alarm limit, which it's unacceptable, really. They'll be in violation and in lots of trouble, basically, with the guys that they report to. I'm going to allow this to run for just a second more. I want to get about 3 hours of control in the DCS, and then I'll flip it over to Griffin control, kind of highlighting how we implemented enhanced control or improve their overall performance of the system. Some things that I'll point out here is in Griffin, we can build tuning screens or monitoring screens. That's everything that we're viewing right here. I have a display of what weekly averages are doing on my actual control display, showing current values of emissions, averages. I can also change things. So if I wanted to change, say, the target of my DCS control in this simulation, all I have to do is double click that box, type in 0.7 instead, click update, and now the application is using that value. There's no need to go in and recode anything. And this is a really useful feature for engineers on site. They want to make a change to how the system's behaving. All they have to do is click a couple of times and click update, and now the system has changed and it's actively using that difference. So we're 3.5 days right now. I'll switch over to Griffin control, and you're going to see immediately the behavior of the pack change. And so rather than immediately responding to fluctuations in mercury, our system recognizes that this is the value that really matters. And so there's no need to start chasing mercury around and upset the process by realizing high opacity measurements and values when there's plenty of room on the value that we're concerned with. You see, even though mercury is higher at the moment, our 30-day average, which is also this green line down here. You can't even see, it's indiscernible, the change to it because of these couple of moments of high mercury. We'll let this evolve for just a moment as well, while I go ahead and show you the actual logic that's being carried out right here. Just like Ricky showed, this is the screen where all of this is developed. So in this system, I'm running the simulation, pulling in data from the data generation application. But then I do really just some data maintenance. I set up these tuning screens and generate displays, calculate some averages, all in this graphical interface. I perform this what if calculation, which tells me, well, if mercury were very high, oh, that's the wrong, sorry, I have two of these windows open. But this tells me what would the average do if mercury was very high for 4, 12, and so many hours. And then the actual control that's going on is all right here. You can see everything that's happening right here. It's deciding, is Griffin on? If Griffin is active, then it comes down. And when it's time to make a control movement right here, it'll go through this upward path and it'll decide, is opacity high? What's my averages doing? And you see right there, it decided to not make a change. Everything was okay. Opacity's not too high. My mercury's looking okay. Importantly, my 30-day average is still just fine, as well as my daily average. So there's no need to potentially upset this process and realize higher opacity because my mercury is doing okay. See right now we're not quite to the same number of hours as the DCS. Our mercury is a little bit higher on average so far, but our opacity is much lower. Our cost of our pack, we'll let this get caught up here, but we're going to end up using less pack while still achieving satisfactory control. And this concept right here is what I'll show you through those 30-day evolutions that are being carried out on the other application. I'll give this just a moment to catch up so we can confirm that in 3 hours, we're going to have a lower pack usage and a lower pack cost. And while that, so far, you see there's been no need to adjust the pack feed rate because just the process itself, mercury is coming out. Something to do with the combustion process, with the coal, the fuel that's being burned. There's less mercury in it, so there's no need to, as I mentioned, upset the process itself. So yeah, you see right here, we've saved a couple $100 in 3 hours of operation. You extend that out to what happens in 30 days, which is what this system is working on right here. So this is that fast version. Let me back it up just a little bit. So here we have 30 days of elapsed DCS control, and this process has 26% of the time had opacity and alarm. And we've spent just about $185,000 on pack. That's using a cost of about $1,800 a ton. We'll let the Griffin version get out to 30 days. So far, it's a week. We've got a little bit more time to go here. But on average, we're a little less on pack usage on our 1-day pack. Our total pack in a single day is about 2,000 pounds less, about a ton less. So that right there is $1,800 saved just in 1 day. And what's even more important is this difference in opacity. We're only 3% of the time in Griffin control above that 21%, which is much fewer violations. EPA's happy, the plant's happy, everything's operating correctly as we want it to. What's also noteworthy here is that so far we're looking at only 10 days compared to 30 days, but our mercury is even lower. We've used less pack. It's cost us less. We have less opacity violations, and our mercury is even lower. And that's again just leveraging the knowledge of the process. using relatively simple control techniques, but the ability to capitalize on those process characteristics. One other thing that I'll point out while we let this get up to about 30 days of runtime is just how the rapid prototyping works. Ricky mentioned that he was able in a week's worth of time to develop completely new logic. What I could even do right now, if I wanted to alter how this system controlled, all I would have to do is come up and pick a different control block. So there's as simple of blocks in here as just basic arithmetic that I can add in here. And just for example, if I do 2 times 2, it's very simple. You can do simple arithmetic all the way up to doing particle swarm optimization using neural networks. All of these are just encased in these little blocks up here that I click on, I drag it into the application, and then I'm free to utilize it and structure my control however I wish, whatever best meets the needs of the process. That's another thing that I'll touch on here is this application actually doesn't use neural networks because that's not necessary to realize effective, useful control of this system. It's more simple is better in a lot of cases. And that's especially the case right here, where we just look at what's going on with those different time frame values and implement control based on that. See, we're starting to get closer, about 2/3 of the way, and we're less than half of the total pack used, which we can extend that to say, yeah, we're going to be about 1/3 less on pack usage, 1/3 less on cost, which when you're talking $200,000, that adds up. And that's just in 30 days. Extend that out to a yearly savings. There's a lot of potential for just a simple control change that capitalizes on the flexibility of this Griffin AI Toolkit. A lot of savings, not just in money, but also in emissions and overall process friendliness to the operator. That's one last thing that I'll say here as this wine wraps up. The operators at this site really like this application because in the past it was more or less manually controlled. They would have to go and change the pack feed rate based on where they saw pack to be and mercury to be and opacity. They'd have to go and make a judgment call on, well, I think I need to set pack to this level. And now that's all automated. They don't have to worry about it. It's taking care of that, watching and balancing how each of these constituents are behaving. So they're now free to focus on things that are more important to them and to the process, knowing that this is more appropriately handled. We'll give this just.
You basically have a chain of if statements checking different conditions and deciding whether to bump pack up, bump it down, or leave it alone. Is that correct?
Yep, that's right. So, Ricky, that's a really good point. So first thing it does is it checks, is it time? Is it time to even check on what's going on? And that's this if statement right here. If it's okay to make a change, then go up. Okay, is, are we in a run back type of situation? No. Okay, is mercury and opacity good? The actual sensor values, good quality, because we don't want to use them if they're bad. Okay, they're good. Okay, is opacity high? Is my 1 hour average higher than my target for that? It is, then I'm going to go up here and I'm probably going to end up pulling out pack because opacity is too high. If it's not, now let's check what mercury is doing. What's my 30-day average of mercury look like? And is it lower than my lower limit? Because I don't want to do too much because that'll end up having a bad effect on opacity. It's just like Ricky said, there's this chain of checks that this process does to decide how do I want to actually control the process. It can check multiple things as well. Is my 1 hour average above a target as well as my 24-hour average? So my 1 hour and my 1 day average, are they above target values? If they are, then I need to add pack because I need to pull mercury down. But if they're lower than a certain level, I can pull pack out and try to help opacity better. So a really good point. I appreciate that, Ricky. That's one feature that we use a lot, is these chained if statements, or these chained checks on the process to decide how to implement control. You see over here, we finished up. So 2 30-day periods of comparable operation. We're about right around $60,000 less in pack using this $1,800 a ton value. We have less or a lower average opacity, less time spent above our alarm period, only 3% of the 30 days compared to 26%. And actually our mercury was even lower than when the DCS was simply driving it, trying to maintain a 0.8 set point. So again, showing how the Griffin AI Toolkit allows a lot of flexibility in how you develop control and how a process is managed. So I'm going to go ahead and open back up our PowerPoint, and I believe we're really to our question and answer portion or discussion of our webinar here. So those of you who have joined since we began our webinar, everybody or attendees are muted at the moment. Please just send a message to the chat box if you'd like to speak, and I'll enable your microphone. So with that, I'll open it up to anybody who wants to ask questions or make comments or anything of that nature. We have about 10 minutes or so.
There should also be a button to raise your hand if you want to make a comment.
Yeah, good point. If I see a hand come up in anywhere, I'll enable your microphone as well.
Were you going to talk about getting hold of the toolkit?
Yeah, yep. Maybe I'll do that, yeah, while we are waiting for a few questions or letting people think about what we've discussed so far. So we have a couple of different methods that you can get a hold of a version of the toolkit to experiment with it for yourself. The first is we have available on the cloud a ready-to-go software installation, and we call it our Griffin Sandbox, really somewhere for anybody to get on, play around with the system, and experiment with dragging and dropping blocks and control logic. We also have on this sandbox some preloaded applications. One's a cooling tower optimization system. Another is just a representation of hitting a baseball with a bat. So not a process control application, but something that's pretty familiar, I would imagine, to most people. It allows you to simulate, given some characteristics of how the ball is thrown and some physical indications of the system, how the ball will be hit and how it'll fly through the air, things of that nature. We'll also in time have both of these applications, this reheat furnace demo and the mercury pack control system, available on that sandbox. Is to gain access to that, all you have to do is go to this website link, Griffin Open Systems Sandbox Environment. If you just go to Griffin Open Systems and click on Try It Now or contact us, there's a link to submit a request to enter the sandbox. And really all that happens from there is we receive that request and we'll send to you the login credentials, and you'll have about a week or so that you can log into that remote server, play with those applications, or you're even free to load in your own data sets and experiment with neural network modeling on those data sets, or developing control logic around whatever's in the data set you load. The full functionality of the system is available on that sandbox. So a really good and easy way to immediately start working around and experimenting with the sandbox. Other method that we have is we can send you your own trial version of the software. This you would install on your own machine, your own laptop, your own desktop. That's another good point is Griffin doesn't require any special hardware, really. All you need is a laptop. I'm doing this on my desktop machine right now. I would imagine Ricky as well did all of his demonstration on a desktop or a laptop, just a typical PC. And so we can send you a trial version of the software that you can install on your system, and then you can play around with it there. We'll provide you with a couple of kind of jump starter applications, and then you can go ahead and do whatever you'd like to from there. Besides that, if you have any other questions or want to request anything in particular, feel free to just email us at either of these two email addresses, info or support@griffinopensystems.com. We try to make it as easy as possible to get the system in your hands, as that's really where it becomes apparent the benefits, or so to speak, you kind of get hooked on being able to do these advanced or these beneficial changes and system developments with very little barrier to entry.
Any final comments? Brad, you want to jump in and say anything?
Oh, no, other than thank you for putting together the presentation material, and thank you to the participants to come in and listen.
Indeed.
I think I saw one new attendee just kind of jump in just recently, so I'm just going to real quick repeat what we've talked about right here, and being able to gain access to your own version or your own copy of Griffin to experiment with it and play with it. We have the sandbox environment, which is basically just request access to a server on the cloud. All you have to do is remote desktop into this system, and then you're free to play around with a working installation of this Griffin AI Toolkit. There's some preloaded applications on there that you can immediately start to see and work with how the system runs, or you can request your own trial version of the software, which we'll send to you and you load on your own machine. Just access or communicate with us through Griffin Open Systems in the contact us portion of that site, or feel free to just email us. Both of these email addresses go to the whole Griffin team, and so somebody will get back to you rather quickly. The other thing that I should mention is that if you're joining us late, or if you want to go back and see some of the stuff that we've talked about here, we're going to load up a copy of this recording onto the website. So this whole webinar and discussion will be available there, but you'll have it on demand at any time if you want to go back and look at key things that were talked about, specifics, or if you just want a refresher on some of the things we've talked about, or to see these links again. Feel free to find that on the griffinopensystems.com website. I'll make a last call for questions. Please just throw a message into the chat box and I can enable your microphone. And if there aren't any other questions, I'll go ahead and close us out. And just again, thank you all for spending an hour with us here talking about the toolkit and Griffin. I hope you were able to see some interesting things, see some unique applications of adavariant artificial intelligence control, and maybe get some ideas for how you may be able to possibly use it yourselves to help you in whatever systems you have, be it steel industry or power production, or I've actually even used Griffin for personal projects and finances. There's a lot of capability in the different features inside of Griffin for modeling as well as process control and decision making. So again, appreciate everybody for being here. I'll go ahead and close this out. Again,
Thanks, Jake. Thanks to everyone.
Take care and hope to hear from you guys soon.